Good day everyone. Welcome to my YouTube channel, Usano-Goldie RL Marquez. This is differential equations, first order first degree ordinary differential equations. In this video, I will be discussing exact differential equations. The method that I will be using in solving exact differential equations in the examples is the commonly used method, which is based on the definition of an exact differential equation. When is a differential equation said to be an exact differential equation? A differential equation of the form m of xy dx plus n of xy dy equals 0 is said to be an exact differential equation if there exists a function f of xy having continuous partial derivatives such that partial derivative of f with respect to x is equal to m of xy, which is the coefficient of dx, and partial derivative of f with respect to y is equal to n of xy, which is the coefficient of dy. For instance, the differential equation 6xy minus 3 quantity dx plus 3x squared plus 2y quantity dy equals 0 is said to be an exact differential equation since there is a function f defined by f of xy, which is equal to 3x squared y minus 3x plus y squared, such that its partial derivative, that is partial derivative of f with respect to x, is equal to 6xy minus 3, which is the m, and partial derivative of f with respect to y is equal to 3x squared plus 2y, which is the n. It's not easy to find a function f satisfying these two conditions, but what is the significance of these two conditions relative to the exactness of m dx plus n dy equals 0? Let's see. From the definition of exact differential equation for m of xy dx plus n of xy dy equal to 0, there exists f such that partial derivative of f with respect to x is equal to m and partial derivative of f with respect to y is equal to n. Let's see what condition we can get out of this in relation to this differential equation. Taking the partial derivative of m with respect to y, that is equal to partial derivative with respect to y of partial derivative of f with respect to x, and that is equal to second partial derivative of f with respect to x, then with respect to y. Also, partial derivative of n with respect to x is equal to partial derivative with respect to x of partial derivative of f with respect to y, and that is equal to second partial derivative of f with respect to y, then with respect to x. From differential calculus, these two mixed partial derivatives are equal as long as they are continuous. But the left side of this equation is equal to partial derivative of m with respect to y, while the right side is equal to partial derivative of n with respect to x, which is a necessary condition for m of xy dx plus n of xy dy equal to 0 to be exact. In most textbooks on differential equations, it is shown that this is not only a necessary condition for this to be exact, but also a sufficient condition. So this means this equality between partial derivative of m with respect to y and partial derivative of n with respect to x is an if and only if condition. Hence, we come up with the following test for exactness. Let m and n have continuous partial derivatives. The differential equation m of xy dx plus n of xy dy equals 0 is an exact if and only if partial derivative of m with respect to y is equal to partial derivative of n with respect to x. Let us illustrate this test for exactness by the following examples. Example number 1. Test the differential equation 6xy minus 3 quantity dx plus 3x squared plus 2y quantity dy equals 0 for exactness. So first we identify m, that is 6xy minus 3. N is equal to 3x squared plus 2y. Taking the partial derivative of m with respect to y, we get derivative of 6xy. We hold x constant here. So derivative of y1 times the constant 6x. Derivative of negative 3, 0. Hence, partial derivative of m with respect to y is equal to 6x. For partial derivative of n with respect to x, we hold y constant. So, derivative of 3x squared relative to x, that is 6x. Derivative of 2y relative to x is 0. Hence, we have 6x as partial derivative of n with respect to x. Since these two partial derivatives are equal, therefore, the given differential equation is exact. Example number 2. Test the differential equation y e to the xy plus y sine x plus 3x squared minus 2xy squared quantity dx plus x e to the xy minus cosine x minus 2x squared y quantity dy equals 0 for exactness. We identify m as y e to the xy plus y sine x plus 3x squared minus 2xy squared, while this is the n. Taking the partial derivative of m with respect to y, we hold x constant. So this is considered product relative to y. So derivative of this, the first, derivative of the second is e to the xy, but derivative of xy is equal to x, plus the second, e to the xy, derivative of y is 1. So, the derivative of the first term is y e to the xy times x plus e to the xy. For the second term, derivative of y is 1 times the constant sine x. Hence, we have simply sine x. Derivative of 3x squared 0. For the last term, derivative of negative 2xy squared is 2 times negative 2, that is 4, times x, y. So, negative 4xy. Simplifying, we get xy e to the xy plus e to the xy plus sine x minus 4xy. N of xy is equal to x e to the xy minus cosine x minus 2x squared y. Taking the partial derivative of n with respect to x, we get, for the first term, this is considered product. The first derivative of the second plus the second derivative of the first. So, we have x e to the xy, derivative of xy is y, plus e to the xy, derivative of x is 1. For the second term, derivative of cosine x is negative sine x, times negative, we have positive sine x. Derivative of x squared is 2x times negative 2y, so we have negative 4xy. Simplifying, we have xy e to the xy plus e to the xy plus sine x minus 4xy. Since these two partial derivatives are equal, the given differential equation is exact. Example 3. Determine the value of the constant k so that the differential equation 2x tangent y plus 12x squared y to the fourth minus 2x quantity dx plus x squared secant squared y plus kx cubed y cubed plus 12y cubed quantity dy equals 0 is exact. First, we identify m and n. So, m is equal to 2x tangent y plus 12x squared y to the fourth minus 2x, while n is equal to x squared secant squared plus kx cubed y cubed plus 12y cubed. Taking the partial derivative of m with respect to y holding x constant, we have derivative of tangent y, that is secant squared y, times 2x, plus derivative of y to the fourth is 4y cubed, times 12x squared, we have 48x squared y cubed. Derivative of negative 2x is 0 because x is constant. Partial derivative of n with respect to x, we have derivative of x squared is 2x times the constant secant squared y, plus derivative of x cubed is 3x squared times the constant, so we have 3k x squared y cubed, plus derivative of 12y cubed 0 because y is considered constant. For this differential equation to be exact, partial derivative of m with respect to y must be equal to partial derivative of n with respect to x. Hence, we have 2x secant squared y plus 48x squared y cubed, that is partial derivative of m with respect to y, equals 2x secant squared y plus 3k x squared y cubed, that is partial derivative of n with respect to x. Comparing this left and right side term-wise, we have this term is the same with the first term on the right. This second term on the left must be identical to the second term on the right. Hence, 48 is equal to 3k. Solving for k, we have 16. So, therefore, for this differential equation to be exact, the value of k must be 16. Example number 4. Determine the most general function m of xy so that m of xy dx plus y sine x minus x e to the y minus 2x squared y quantity dy equals 0 is exact. First, let us identify n, that is equal to y sine x minus x e to the y minus 2x squared y quantity dy. Taking the partial derivative of n with respect to x, holding y constant, we have for the derivative of sine, that is cosine x times y, which is constant, so y cosine x. Derivative of x is 1 times the constant, we have negative e to the y. Then we have derivative of negative 2x squared y, so that is equal to negative 4xy. So that is derivative of x squared 2x times negative 2y, so we have negative 4xy. For this differential equation to be exact, this partial derivative of n with respect to x must be equal to partial derivative of m with respect to y. To solve for m, we get it from the integral of partial derivative of m with respect to y quantity dy, but partial derivative of m with respect to y is equal to y cosine x minus e to the y minus 4xy. Hence, we have integral of y cosine x minus e to the y minus 4xy quantity dy. So, m is therefore equal to cosine x times the integral of y dy, because cosine x is constant, minus integral of e to the y dy minus in 4x, again 4x is also constant, integral of y dy. Integral of y dy is y squared over 2 times cosine x. Integral of e to the y dy is e to the y. Integral of y dy is y squared over 2 times negative 4x plus some constant of integration denoted by q of x. Simplifying, we get 1/2 y squared cosine x minus e to the y minus 2x y squared plus q of x. So this is the most general function m of xy, so that the given differential equation becomes exact. How to solve an exact differential equation? So this is the method of solution. Let m of xy dx plus n of xy dy equal to 0 be an exact differential equation. This means that there is a function f such that partial derivative of f with respect to x is equal to m of xy, which is the coefficient of dx. And partial derivative of f with respect to y is equal to n of xy, which is the coefficient of dy. Hence, this differential equation becomes partial derivative of f with respect to x dx plus partial derivative of f with respect to y dy equal to 0. But this left side is the total differential of f. Hence, we have differential of f of xy equals 0. To solve for f, we integrate its side. So integral of differential of f of xy equals k. So we have f of xy is equal to k. And that is the general solution of this exact differential equation. F of xy is equal to some constant k. Again, k is any arbitrary constant. From such method of solution, we come up with the following steps in solving an exact differential equation. Given exact differential equation m of xy dx plus n of xy dy equal to 0, so the first step is to identify m of xy or n of xy and then find f of xy. If m is chosen, f of xy is equal to the integral of m of xy dx plus t of y, where y is held constant. If n is chosen, f of xy is equal to the integral of n of xy dy plus q of x, where x is held constant. Second step, compute the first partial derivative of f with respect to y if m is chosen, or partial derivative of f with respect to x if n is chosen, of the function f of xy obtained in step 1. So, if m is chosen, we compute partial derivative of f with respect to y, which is equal to partial derivative with respect to y of the integral of m of xy dx plus t prime of y, which is equal to n of xy. Or, if n is chosen, we compute partial derivative of f with respect to x, which is equal to partial derivative with respect to x of the integral of n of xy dy plus q prime of x, but this is equal to m of xy. Third step, solve for t prime of y if m is chosen in step 1, or q prime of x if n is chosen. So from the equation, partial derivative of f with respect to y equals n of xy, or partial derivative of f with respect to x, which is equal to m of xy, derived in step number 2. So hence we have t prime of y is equal to n minus partial derivative with respect to y of the integral of m of xy dx, or q prime of x is equal to m of xy minus partial derivative with respect to x of integral of n of xy dy. Fourth step, find t of y or q of x, omitting the constant of integration from equation in step 3. So t of y is equal to integral of t prime of y dy, but t prime of y is equal to this difference, that is n of xy minus partial derivative with respect to y of the integral of m of xy dx, or q of x is equal to integral of q prime of x dx, but q prime of x is equal to this difference, that is m of xy minus partial derivative with respect to x of this integral of n of xy dy. Fifth step, substitute t of y or q of x obtained in step 4 to the equation in step 1. And then the last one, write the general solution, which is f of xy equals k. So let us apply those steps in solving exact differential equations in the following examples. Solve the differential equation 6xy squared minus 8x cubed quantity dx plus 6xy plus 3y squared quantity dy equals 0. First, let us identify m of xy and n of xy. So m is equal to 6xy squared minus 8x cubed, while n is equal to 6x squared y plus 3y squared. Getting the partial derivative of m with respect to y, we have derivative of y squared 2y times 6x, so we have 12xy. So this is 0. Partial derivative of n with respect to x, so we have 2x times 6y, we get 12xy. This is 0. Since these two partial derivatives are equal, the given d is exact. Find the function f. Let's determine f from the integral of m of xy dx plus t of y. But m is equal to 6xy squared minus 8x cubed. Integrating this relative to x, holding y constant, we have x squared over 2 times 6y squared minus 8x to the fourth over 4 plus t of y. Simplifying, we have 6 over 2, that is 3, x squared y squared minus 8 over 4, so 8 over 4 is 2, so we have negative 2x to the fourth plus t of y. Let's compute partial derivative of f with respect to y from this f obtained. So f of xy is equal to 3x squared y squared minus 2x to the fourth plus t of y. Differentiating this partially with respect to y, we get, for the first term, we have 6x squared y. Second term, this is 0 because x is constant, plus t prime of y. So, partial derivative of f with respect to y is equal to 6x squared y plus t prime of y. But this is equal to n of xy. So, next is solve t prime of y. And then find t of y. So, from this equation, we have 6x squared y plus t prime of y equals n of xy. But n is equal to 6x squared y plus 3y squared. Solving for t prime of y, so this is cancelled, getting t prime of y equals 3y squared. Solving for t of y, we integrate this left side relative to, this right side relative to y. So getting y cubed over 3 times 3, so we have y cubed, omitting the constant of integration. So f of xy therefore is equal to 3x squared y squared minus 2x to the fourth plus y cubed. The value of t of y is y cubed. So hence, the general solution is given by f of xy, which is equal to some constant k. So we have 3x squared y squared minus 2x to the fourth plus y cubed, that is f of x, equals, I'm going to choose my k as c. So my constant of integration is c. Hence, my general solution is 3x squared y squared minus 2x to the fourth plus y cubed equals c. So this is the general solution to the given differential equation. Example 6. Solve the differential equation 4x squared y cubed minus 5y to the fourth plus 2xy to the fifth minus x to the fourth dx plus 4x cubed y squared minus 20x y cubed plus 5x squared y to the fourth plus 2y quantity dy equals 0. So let's see if this is an exact differential equation. So we identify m and n. Taking the partial derivative of m, we have 12x squared y squared. So again, differentiating this partially relative to y, we hold x constant. So derivative of y cubed is 3y squared times 4x squared. We have 12x squared y squared minus derivative of y to the fourth is 4y cubed times 5 negative 20y cubed plus we have 5y to the fourth times 2x 10xy to the fourth, and lastly we have 0. So this is the partial derivative of m with respect to y. For partial derivative of n with respect to x, so holding y constant, so this is 3 times 4 12x squared y squared minus derivative of x is 1, so times negative 20y cubed. Here 2 times 5, that is 10x y to the fourth. Comparing, they are equal, hence this DE is an exact differential equation. So we can proceed. So we find the function f from the integral of, so what I considered is m. Although you can consider also n. So we have integral of 4x squared y cubed minus 5y to the fourth plus 2xy to the fifth minus x to the fourth quantity dx plus t of y. Integrating this term by term relative to x, holding y constant, we have x cubed over 3 times 4y cubed minus x times 5y to the fourth plus x squared over 2 times 2y to the fifth minus x to the fifth over 5 plus t of y. Simplifying, we get 4 thirds x cubed y cubed minus 5xy to the fourth plus x squared y to the fifth minus 1/5 x to the fifth plus t of y. Compute partial derivative of f with respect to y from this computed f. So relative to y, x is constant. So we have 4x cubed y squared. So this is 3y squared times 4x cubed minus 4 times 5, that is negative 20, then x y cubed plus 5x squared y to the fourth minus 0 because x here is considered constant. So derivative of t of y is t prime of y. But this is equal to n of xy. Solve for t prime of y and then find t of y. So we have 4x cubed y squared minus 20xy cubed plus 5x squared y to the fourth plus t prime of y. So that is equal to n of xy. Solving for t prime of y, we have t prime of y is equal to 2y. This is cancelled with this. Negative 20 is cancelled with negative 20xy cubed. 5x squared y to the fourth is cancelled here. So t prime of y is equal to simply 2y. So getting t of y, we have integral of 2y dy. So that is equal to y squared, again omitting the constant of integration because we want only a particular t of y. Hence f of xy is equal to 4 thirds x cubed y cubed minus 5xy to the fourth plus x squared y to the fifth minus 1/5 x to the fifth. T of y is y squared. So this is our f. So the general solution therefore is given by f equated to some constant k. So we have this f equals 1 over 15 c. The reason behind of choosing 1 over 15c for my constant k is that when I simplify this, meaning by when I multiply it by 15, this will be simply c. So we get, for my simplified answer, we have 20 x cubed y cubed after multiplying by 15. 15 divided by 3 is 5 times 4. So we have 20x cubed y cubed minus 45xy to the fourth times 15, 15x squared y to the fifth times 15, negative 3x to the fifth times 15, 15y squared equals c. So this is the general solution of the given exact differential equation. 7. Solve the differential equation x squared y to the fifth plus 4y e to the x minus 3 cosine x quantity dx plus 5 thirds of x cubed y to the fourth plus 4 e to the x plus 2 sine of y quantity dy equals 0. So let's see if this is an exact differential equation. So this is m and this is the n. Getting the partial derivative of m with respect to y, holding x constant. So we have 5x squared y to the fourth plus, this is 1, so getting 4 e to the x only, 0 for the derivative of this. For partial derivative of n with respect to x, we have y constant, so 3 cancelled with 3, so we have 5, then x squared times y to the fourth. Then here, the derivative of e to the x is e to the x relative to x, so times 4, so plus 4 e to the x. So sine y is considered constant because y is held constant. So 2 sine y, the derivative is 0. Comparing, they are equal. Hence, this DE is an exact differential equation. So let's proceed. So this time, I consider solving f from n. So integral of m dy plus q of x. So this is my m. Integral relative to y holding x constant. So we have x to the third times 5 thirds. Integral of y to the fourth is y over 5, y to the fifth over 5. Plus, so relative to y, the integral is y times the constant for e to the x. Integral of sine y is negative cosine y times 2, negative 2 cosine y, plus this constant of integration, which is in terms of x. So let's determine this value of q of x, which is the unknown in f. So to compute that, we have to first compute partial derivative of f with respect to x. So from here, holding y constant, so getting the derivative, we have 3x squared times y to the fifth divided by 3. So x squared y to the fifth. So derivative relative to x of e to the x is e to the x times 4y plus derivative of this relative to x, this is considered constant, so this is 0. So plus q prime of x. But this is equal to m of xy. Solving for q prime of x and then find q of x. So we have x squared y to the fifth plus 4y e to the x plus q prime of x. So this is our f of partial derivative of f with respect to x, which is equal to m. So, but m is equal to x squared y to the fifth plus 4y e to the x minus 3 cosine x. So this is cancelled together with this. So q prime of x is simply equal to negative 3 cosine x. Integrating negative 3 cosine x relative to x, we have integral of cosine is sine x times negative 3. So negative 3 sine x for q of x. So we omit the constant of integration because we want only a particular q of x. So we know already q of x. So replacing this by its value, we have f of x is equal to 1/3 x cubed y to the fifth plus 4y e to the x minus 2 cosine y minus 3 sine x. Hence, the general solution is f of xy equals some constant k. So let me choose my k as 1/3 c, so that if I multiply this by 3, so this right side will simply become c, because I want my final solution having arbitrary constancy. So multiplying by 3 the left side, we get, so this is our f of x, by the way. So this is x cubed y to the fifth times 3, 12y e to the x times 3, negative 6 cosine y times 3, negative 9 sine x equals c. So that's the general solution of the given differential equation that is exact. So that's the last for this lesson. So here are some exercises that I prepared for you so that you can practice. Test for exactness the given differential equation. If it is exact, then solve. So this is number 2 and then number 3. You can apply those steps that were mentioned in solving this. In the continuation of this video, I will be showing 4 other methods of solving exact differential equations. I advise that you check out that video as well in order to give you other options of solving exact differential equations. It's all up to you to choose which method you wish to use for showing your solutions. To give you in advance an idea of how these methods look like, so here they are. Comparison of f's, direct formula, shortcut method, and then the last one, method of grouping. again. So in the next video, which is the continuation of this, I will be tackling the other methods of solving exact differential equations. Thank you for watching. Please don't forget to subscribe to my YouTube channel. So we have Usano-Goldie, R.L. Marquez.